It's a great pleasure to be here. A building and a room full of history, full of wonderful talks about science. My accent will not tell you, but I am a Brit. I was born here, born in Edinburgh, and I was an undergrad at Imperial College and then a PhD student in Edinburgh. And then I left because I'm an astronomer, and it might have escaped your attention, but there's a lot of clouds in the UK, and so I went to Arizona, where the skies are clear about 300 I don't want to make you feel bad, about 310 days in the year we have blue skies and then dark skies at night. So I've been there ever since for my whole career. And I want to talk about a subject obviously of great interest generally and topically, because it's in the news pretty much every week, and it's been very much in the news in the last month or so. Black holes. And the book that I decided I needed to write based on black holes. It's my 8th book. If you care for other topics, I've written about cosmology and astrobiology. I've written a book about teaching cosmology to Tibetan monks in a program started by the Dalai Lama. That's a slightly strange book. And a science fiction novel somewhere in there too. Tonight I'm talking about black holes, and I guess the message up front is going to be that they're just as exciting and enigmatic as you might have thought they were and hoped they were, but we've learned a lot about them. And so it's at that wonderful cutting edge of science. Murray Gell-Mann, who was a Nobel Prize winner in physics, once said, research is what I do when I don't know what I'm doing. And you can just smile and say, well, if you have a Nobel Prize, you can say anything and get away with it. What he meant was that science, and this subverts the bad archetype or stereotype about science and scientists, which nobody in this room, of course, adheres to, but out there in the polis, in the public place, it's held, that science is sort of cut and dried facts, and it ends up being a little dull. Gell-Mann was saying that science is the edge between what we know and what we don't know, and the implication of that is that you might be wrong at any point. The implication is of great uncertainty. It's a very dynamic thing to be at the edge of knowledge. And that's why research is fun. That's why I do research, and that's why black holes are still fun, because we're at that cutting edge is everywhere with black holes. There are things we know, things we don't know, things we thought we knew that turned out to be wrong, and so on. So it's a fun subject in that way. We're going to meet 2 of the fathers of black holes, well known to everyone, of course, Einstein and Hawking. And I'm going to start by pointing out that the concept of a black hole actually predates general relativity and Einstein by over 100 years. John Mitchell, who was an amateur astronomer and physicist, there were no professional astronomers in the late 18th century. He was a clergyman. He thought deeply about physics and philosophy and mathematics, and he imagined a star that was large enough or massive enough that the escape velocity that every object with gravity has equaled the speed of light. And logically, that's a dark star. Now, you can't formally understand black holes with Newton's theory of gravity, which is all he had available to him, but it's an interesting step in a direction of imagining dark stars in the universe, things that where light cannot escape. And so, again, 100 years before the theory that really lets you understand them, the idea is out there. So that's the very earliest inkling of black holes. Of course, the real understanding of black holes starts with relativity, and it starts with Einstein, he's owned by the popular culture. He's become a creature, of culture rather than of physics and astronomy. In his day, clearly the most famous scientist, and still one of the greatest scientists in history, instantly recognizable, very elevated in public esteem. He was offered and turned down the presidency of the state of Israel. He was celebrated in many ways, and with good reason. So we can't talk about black holes without talking about relativity. You're a sophisticated audience, so I think I can hit you with the full horror of it, which is 10 second-order partial coupled differential equations, which I will ask you to solve, and we'll take answers here before you're allowed out of the room. And that, even for physics students, gives them the sweats, the night sweats. So I took a general relativity course. It was not that much fun. I'm not a mathematical physicist. But relativity is conceptual. So let me give you the conceptual understanding of relativity. And it starts with an awareness of Einstein based on a coincidence. Physicists hate coincidences. When there's something that's a coincidence, either numerical or physical, it means we don't understand something. The coincidence that Einstein was struck by was the fact that the inertial mass of an object, that's its resistance to a change in its motion, if I push something, it doesn't want to be pushed, and we can imagine this is a perfectly smooth surface like ice. It will still resist a change in its motion. Gravity is not really involved here. It's keeping the book on the table, but it's not resisting the motion sideways. That's the inertial mass. The gravitational mass is the mass that leads it to fall in the Earth's gravity. Those are really quite different things conceptually, and yet numerically those masses are identical, not known with this precision, but now to 1 part in 1,000 trillion. That begs for an explanation. Einstein conceptualized this with a little thought experiment. He said, well, if you imagine these two situations illustrated, there's no way you can distinguish these experimentally. Someone in a spaceship that's being accelerated with no windows, they can't see their situation, accelerated 9.8 meters per second into space. And then someone in a lift on the Earth's surface, again, they can't see out, and objects being dropped, experiments done, you couldn't tell the difference. One situation clearly involves gravity, the lift sitting there on the floor, held down by the Earth's gravity, and the other, no gravity at all, deep space. There doesn't have to be any object there, it's a rocket. He also realized that these two situations are indistinguishable. One is fairly innocuous. It's an astronaut floating around in deep space inside a spaceship. In the space station, you would see the same thing. And there's no gravity involved here. In deep space, there might be no object anywhere near. It's just zero gravity. These are just floating things. The other is much more ominous. The cable on the lift is broken. The person is plunging to their death, and they're floating around in the lift. And Einstein, sadist that he was, said this is the happiest thought of his life. This awareness that these two situations are indistinguishable. So general relativity is a statement that there's nothing special about acceleration due to gravity relative to any other force, like chemical rockets or something like that, when obviously those things are totally different. And that simple awareness led him down a road that led to a mathematical theory of gravity based on a very different concept of gravity, the concept of curved space-time. Newton's gravity theory was based on objects that exerted forces over a distance. And the fact that this happened in the vacuum of space, apparently instantaneously, was a little puzzling. And when Newton was asked about this, he said, I frame no hypothesis. He didn't actually know. There was some deep philosophical underpinning of his theory that were still mysterious. It worked, you can calculate it. It's how we send people to the moon and how we launch rockets still. Einstein got rid of the idea of forces and action at a distance in the vacuum of space and how does that work. And he said, no, mass and energy bend space and time. He'd already hyphenated mass and energy with E equals mc squared, and he hyphenated space and time in general relativity, and he said, general relativity, those horrid 10 partial differential equations, are just equations that relate mass and energy to space and time, the density of mass and energy to the curvature of space and time in 3 dimensions. And it's a very different idea of gravity, and it works. It's been tested, and it works. And I'll show you some of the tests. Some of the early tests in the 1950s involved very subtle experiments because these were done on the gravity of the Earth. And the Earth is a weak gravity object. Black holes that we're going to talk most of the time about are intense gravity objects. So doing these tests is really difficult. But it was done. These were done in the 50s and 60s. And general relativity implies that a clock, a timekeeping piece, runs slower in strong gravity than weak gravity. And that extends to the Earth. And so in principle and in theory and in general relativity, a clock here runs very slightly slower than a clock here. Now this was tested in the 1950s with atomic clocks flown in high-altitude planes compared to an identical atomic clock on the ground. And the timekeeping was slightly different. Clocks are now so good, optical switch clocks are so good that we can measure time working differently in 1 meter in the lab. So, and the precision of this experiment, you can see, is 1 part in 10 to the 19. Incredible physics experiment. Another experiment done also decades ago shows that gravity photons struggle as you can think of them struggling. It's very anthropocentric to do that, but they lose energy, and that's a redshift. So losing energy for light is stretching the wavelength, is redder. It's called the gravitational redshift. And that's also been measured many, many times and in many different ways. So general relativity by the 1960s had been measured, tested in all manner of situations of weak gravity, and had passed every test with flying colors. And that's still a true statement. The most dramatic demonstration of general relativity comes in astronomy when we take pictures of the sky and watch light being bent by space. So if space-time is curved by objects, by mass and energy, then light essentially follows the curvature of space-time. And so it undulates, it moves, it bends, it can be focused by an object just like a lens. Like an optical lens, it could be a lens of mass. And in the Hubble Space Telescope, this is just one of now thousands of pictures that have been taken that show that the cluster, the bright bunch of galaxies in the middle, is a cluster at about 3 billion light years, and the little arcs of light that you can see are arranged roughly in concentric circles around the center of mass of the cluster are much more distant galaxies, 5, 7, 8 billion light years away, and their light has been sheared and amplified, actually, and obviously bent by the intervening cluster. So this is a lens of mass, bending light. Dramatic demonstration that needed imaging from space to see initially. Now we can do it from the ground as well. The techniques are better from the ground to take sharp images, and literally thousands of these pictures have been taken. So mass bends light unequivocally. So what are some of the other differences conceptually between Newtonian gravity and Einstein's gravity? Because if we're going to believe general relativity, we have to believe these differences. Here's a beautiful experiment that was done, a very difficult experiment done in the 90s. It took almost 20 years to get the result. But in Newton's theory, as I've mentioned, space and time are not coupled. Space and time are different things. And really, intuitively, that's what it feels like. Space is the stuff around us and objects fill space, and time is something that flows and never goes backwards, and we experience that they do not seem related. So to hyphenate them is audacious, just in principle. So in Newton's theory, a spinning object or a gyroscope on a satellite around a spinning object, because that's the experiment we're going to talk about, doesn't really care about its larger situation. The space and the time, they don't care about this. In Newton's theory, space was infinite and flat, and time was infinite and smooth and never changed. But in Einstein's theory, these things are now coupled in interesting and subtle ways. And in principle, these are testable. And in this particular situation of the Earth will bend space-time, but very subtly, because it's not a big object. It's not a very dense object either. And so in this two-dimensional analogy, we can imagine it like the surface of a sheet being bent or distorted, space-time around the Earth by the gravity of the Earth. But something else is going on. The Earth is spinning, and that actually leads to a second effect, which is the twisting of the space-time contours. Just think of it like a vortex, like a whirlpool. And in principle, both of those phenomena, the twisting of the space-time contours and the bending of space-time by the Earth, are detectable. And the probe used in this one satellite experiment, called Gravity Probe B, involved a gyroscope, and gyroscopes are always supposed to point locked on one direction in deep space. In Newton's theory, that would not change as the satellite orbits the Earth. In Einstein's theory, the gyroscope is subtly tugged by the curvature of space-time and the twisting of the space-time contours, and you can measure it in principle. So what does it take to make a black hole? Here's a physicalization of it. You would have to crush something like the sun, which is 1.5 million kilometers in diameter, down to the size of a small town, 3 kilometers. And then it would formally be a black hole. It would have an escape velocity that was the speed of light, and nothing could escape, because light is the fastest thing there is. But the same principle is true for any object. Nature does not impose a limit on the size or mass of a black hole. So if you could take the Earth and crush it down to, golf ball sized, then formally it would be a black hole. You could take a rock and crush it down to proton size, and it would be a black hole. So nature, in theory and in principle, can make black holes of any mass and any size. And the question for astronomers, for scientists being empirical, is which of these does nature make? Which actually exist in the universe? The first type of black hole to be proven to exist, the type that was anticipated from the theory, within a few decades of the theory, is the kind of object left behind when a massive star dies. This is not the fate of the sun, because when the sun dies, having lost some of its outer envelope, the 2/3 of its mass that remains will crunch down to a white dwarf, which is a cooling, carbon-rich ember, which is incredibly dense, millions of times denser than the sun now, but formally not the density of a black hole. But a star that started its life 10 times the mass of the sun will lose some mass along the way, and then its core, when all fusion stops, and the fusion, remember, is the only thing that keeps a star puffed up. So the sun is only the size it is because of a balance between pressure from fusion reactions and gravity in. Well, when that equation is broken, because there's no energy from fusion, gravity will win. And so the inexorable victory of gravity in a massive star, in theory, leads to a black hole, because there's no force to resist compression to that dense state. The theory, the calculation of this, so the basis for it is from general relativity and Einstein's theory. The actual calculation emerged from mostly Robert Oppenheimer and Hans Bethe in the 1930s, and it was essentially a byproduct of Oppenheimer's work on the Manhattan Project, figuring out superdense states of matter that are how we generate bombs and fusion. And he used those same calculations to show that logically a massive star should have no force that could resist it turning into a black hole. So from the late 1930s, early 40s, the prediction was there. There should be dead stars that are black holes. Go look for them. Black holes in the theory are very simple. They're incredibly simple objects. They are characterized by an event horizon, which is not a physical boundary. It's an information membrane. It marks the difference between places we can see in the universe and a part of the universe that's sequestered off, that's hidden from our view forever, that nothing can escape from and we cannot see inside. No information can escape. And that has a particular size that scales linearly with the mass of the object. And in the theory, the black hole also has something a little more monstrous, a singularity. So if you calculate in general relativity, there's a cusp of density that's infinite at the center, and that's a singularity. And that's a problem. Anytime in physics you get an infinity coming out of your calculation for physical quantity, it means you don't understand something. And Einstein, or actually Hawking, has said famously, this means that black holes contain the seeds of their own demise. So everyone from Einstein through Hawking to the present day is aware that the theory of black holes is incomplete because singularities are nonsensical. They're also impossible to inspect because they lie inside the event horizon. So all we can do is speculate. But the theory has a problem just because they're predicted. The other property of a black hole is spin, because the stars that form black holes were spinning. As they collapse, they spin faster, angular momentum conserved, so we would anticipate all black holes in the universe are spinning, and probably very fast. So black holes have mass, they have size, they have angular momentum, and that's it. Very simple objects. And in 1969, Cygnus X1, the brightest X-ray source in the sky in the constellation of Cygnus, was shown with very clever and quite complicated observations to be a binary star system where one member of the binary pair was a giant star, supergiant star, and the other was a black hole sucking material off the giant star, and that material glows brightly. So brightly and so hot that it emits X-rays, enormous amount of X-rays. So the irony of black holes is that, yes, an isolated black hole is black by definition, is invisible by definition. So how do you find them? Answer, you don't look for an isolated black hole. They could be all over the place, we won't find them. Most stars are in binary or multiple systems, so it's anticipated, it's normal, that there are going to be binary stars where one is massive enough to die as a black hole and the other is not a black hole. And that if they're in a tight binary orbit, the black hole will pull material off the normal star, heat that material up, and the heating of that material will be the telltale that there's a compact object. And then you measure the orbital properties of the binary, and by Kepler's laws, don't need general relativity. And if the mass is sufficient and it's a dead star, it has to be a black hole. In the intervening half century, we still only have 50 examples of black holes that are like this. It's not many. It's a pretty thin haul for half a century of work. So it's hard to find black holes. The nearest ones are hundreds of light years away. So we can rule out right away the popular notion in the culture that they're going to eat everything and they're nearby and they're a danger and a threat. They're quite rare because only a tiny fraction of stars are massive enough to die that way. So the nearest examples are going to be far, hundreds of light years away. But we do know examples, and so black holes, to most astronomers, are confirmed as real astrophysical objects. And then we come to the contributions of Hawking. So sadly, the bard of gravity and black holes was lost to us just last year, being in London on sabbatical, actually. Now I'm here for 6 months. I got to visit his grave and, of course, many other illustrious scientists in Westminster Abbey. And what did Hawking add to the conversation about black holes? A lot. Much of this work was done when he was quite young, when he was a graduate student or a postdoc. His singular contribution was the prediction that black holes have another property beyond the three I mentioned, and that last property is temperature. How can a black hole have a temperature? How can anything escape a black hole? Hawking saw that there was a very clever mechanism in physics and in the lab. It's known that spontaneously from the vacuum, from a pure vacuum of space, particle-antiparticle pairs can appear and disappear. That's allowed by Heisenberg's uncertainty principle. So you can steal energy from the vacuum as long as you give it back very quickly. If that happens near the event horizon of a black hole, there's a finite chance that one member of the pair will be lost inside the black hole, the other will escape. And in the aggregate, that is a net loss of either mass, and mass and energy, as we know, are equivalent, or energy. And the radiation from the black hole is called Hawking radiation. It's because this is a very subtle phenomenon. It's a very subtle temperature. The Hawking radiation for a black hole that's a dead star is about 1/1000th of a Kelvin. This is completely unmeasurable in astronomy and may never be measurable, unfortunately. Hawking was kind of sad about this because he realized Nobel Prizes are only awarded for discoveries, not for theories. And he knew that if Hawking radiation were ever detected, he was a lock for a Nobel Prize. But the truth is, it's very, very hard to detect. And the concomitant effect that black holes are slowly losing mass is black hole evaporation. And that's also an incredibly subtle effect. A black hole that's left when a massive star dies will take 10 to the power 68, 1 with 68 years to fully evaporate by Hawking radiation. And again, no way astronomers can ever measure that, probably ever. I mean, certainly not now, and maybe not even in principle. So, but this is a contribution to black hole theory that has various implications, and they're all important. Obviously, the fact that black holes evaporate is important. It means they're not eternal. They are going to eventually disappear. And a logical question is what becomes of the information that was lost in a black hole? And so one of the consequences of Hawking's theorizing was something called the information paradox. And there are different ways to frame it, but it's a big issue. And this is a totally current issue. There are probably 50 or 60 papers a year written right now on information paradox and related issues. And it's something very simple to describe. A black hole is mute to all of the things that went into it. So a black hole that was made of a dead star looks exactly the same and has the same simple monolithic properties as a black hole that's made of all the odd socks that humans or other civilizations ever lost, or made of cats or made of whatever. It doesn't matter. And so black holes have lost information. You could toss books. You could make it a black hole out of books and encyclopedias, and you'd never get that information out. What happens to the information? So this has become the information paradox. It's a problem because a premise of quantum theory is that information is preserved in microscopic interactions. So when you have particle interactions in the lab at a subatomic scale, they can run forward or backward in time, they can involve matter or antimatter, and the information in the interaction is always preserved. It's a premise of quantum physics. This premise is violated by black holes overall, and it's definitely violated at the event horizon. And this is essentially a statement, the information paradox is a statement of the fact that our gravity theory and our quantum theory don't play well together. They are not compatible theories. And we've known this for many years. This is just a particular example of it. And it's led to all sorts of speculations of how you may preserve, maybe the information is preserved, because as we'll see, when things fall into a black hole, their time slows down asymptotically, infinitely. So maybe the information is preserved as matter falls slowly onto a black hole, like a hologram, and it's coded onto the event horizon, if we could somehow extract it, which we can. Maybe it's destroyed in something called a firewall. So there are many theoretical ideas. Like I said, dozens and dozens of papers a year written about this, all unresolved issues in theoretical physics. And signs that black holes still have plenty of juice left in them as theoretical objects of study. Meanwhile, astronomers were busy trying to find out whether nature made other types of black holes, and nature does. Nature makes some amazingly big black holes. Here's an example of how black holes have been found over a range of actually a factor of 1 billion in mass. Incredible. And probably the most dramatic evidence, and I would say the best evidence for any black hole in the universe, better than any of those nearby black holes in binary stars, the first ones to be discovered, the best evidence for any black hole is the object at the center of our galaxy. So what you're seeing here now is it's not a simulation or a cartoon-like animation. These are real three-dimensional orbits of stars near the center of our own galaxy, the Milky Way, 26,000 light years away. And each of these stars is a test particle that's probing the mass at the center. And they're moving really fast. This data spans about 2 decades. This is very hard data to obtain. It was impossible until the early 1990s to get data this good, close to the center. Each star is testing and measuring the mass of the center of our galaxy. And if you do them close enough to the center, they're showing that the galaxy has 4 million times the mass of the sun crushed or contained in an incredibly small space, such that it must be a black hole. And like I said, because the black hole is diagnosed by each of these stars and their orbits, the evidence for this black hole is better than any black hole in the universe. There is no doubt that there's a 4 million solar mass black hole right in the middle of our galaxy. Very exciting. Meanwhile, the Hubble Space Telescope was working, and through the 80s and 90s, in observations that are not as dramatic, they don't prove within the shadow of a doubt the black hole, you drop the slit of a spectrograph on the left over a galaxy, and on the right, the colored lines show the Doppler shift of stars near the center of the galaxy, and you can see the strong blue and red deviations close to the center. Those high stellar velocities are also probes of that central mass of that galaxy. And when you do the math, nearby galaxies have black holes too. And every galaxy that was studied through a period of 20 years with the Hubble has a black hole. So black holes are not special to our galaxy. Why should they be? That would violate the Copernican principle. They're found in every galaxy that we've studied so far. But these galaxies are quiet. Their centers are not especially active or bright. So if these black holes are doing anything, they're probably not eating a lot of material, they're not consuming material, they don't have active accretion. So a puzzle raised by this discovery was if every galaxy has a black hole and there's tons of stuff for them to be accreting, that as we've seen in binary star systems, when that gas is sucked in, it gets really bright and emits X-rays and optical waves and radio waves and everything. Why aren't these black holes doing that too? And the answer seems to be that they're only active about 1% of the time. So every galaxy has a black hole, but each one is only switched on or bright or actively accreting material 1% of the time. And in between, it seems that they blow out enough material that they sort of starve themselves, and that material has to accumulate in the center of a galaxy and trigger a new episode of activity. That's the guess. We don't get to stare at a galaxy and watch it evolve and see them switch on and off. You do it with statistics. And in these studies, it was shown that the central black hole in a galaxy scales very nicely and beautifully, actually, over orders of magnitude with the mass of the old stars in a galaxy. In the Milky Way, that would be the bulge component, the center part of our star distribution. So somehow the galaxy knows about the black hole knows about the galaxy that it sits in. And if you can zoom in on these are radio images, and the galaxy in this case was about the size of the central dot, and it's sending huge jets of plasma, hundreds of thousands of light years, a couple of million light years actually, out into space. If we could zoom in close enough, we'd see there was a spinning black hole. It was accreting material around its equator in a scaled-up version of those binary star systems, and it was emitting jets of plasma very, very close to the speed of light out of the poles and sending it deep into intergalactic space. And radio astronomers made these pictures starting 40 years ago, and now we've seen many examples. And this is what the black hole looks like when it is active, when it's doing something dramatic, as opposed to the one in our galaxy, which is pretty quiet and pretty dark and pretty quiescent. The information that's recent and very exciting from within the last month is, of course, the fact that we now can see the black hole. So the first image of a black hole was made with an array of radio telescopes, essentially treating the Earth as a giant radio telescope, and so getting the angular resolution, the sharpness of imaging, as if you had a telescope that was 10,000 kilometers across by combining information from radio dishes across the planet. One of those telescopes was at my observatory, and some of the lead investigators in the Event Horizon project are at my university, so I've heard about this, and I saw the images. I was sworn to secrecy like a few other people before this image was put out just a few weeks ago. And this is the M87 galaxy, Messier 87, and this is a direct image of the event horizon. The dark circle is the event horizon. The glowing ring is the gas around the black hole that's being heated up by gravity energy, basically. The asymmetry is because the black hole is rotating and the gas on the lower part is coming towards us and is Doppler boosted. Its radiation is boosted by the Doppler effect to be brighter, and the radiation on the top is moving away, or the top part is moving away from us and is dimmer. And all of this is understood by relativity. And here's a zoom in. So this shows the biggest scale of M87, which is sending jets way out into space, like that other example I showed. And then you zoom in on the right-hand side, closer and closer and closer, until you get to a scale that's about a few light weeks. And that's when you see the black hole. And this data has already shown some amazing things. There's things that it can't do, but it's a simple image. It doesn't look that impressive. But it's already been used to show what the spin and the orientation of the black hole is, because you can run simulations and models and see whether the models fit the ring that you observed and its asymmetry and its brightness. And these models have also measured the mass to be 6.5 billion times the mass of the sun. So remember, that's 1 billion times more than the mass of those stellar black holes that were the first to be predicted and the first to be measured. It's a spectacular black hole. And because even astronomers get blasé about big numbers, I just want to remind you how spectacular it is. But first, the fact that black holes do not overwhelm the universe. If you make a pie chart of the universe, dark matter and dark energy dominate. That's another talk. I mean, that's research I work on too. And it's the biggest question in cosmology, what are those two things? But black holes, if you can see, are 0.005% of the universe. So as spectacular as they are, they're a little minor component of the universe. Each galaxy has a black hole that's roughly 0.1% of its mass. So they don't dominate the budget of the universe in mass. But they are spectacular because when they are accreting, when they are chewing in material, they're superb gravity engines. That's the way we would refer to them. They can convert mass into radiant energy with 40% efficiency, by which I mean equals mc squared, 40% efficient. The sun and all stars are less than 1% efficient. So big black holes are dozens, nearly 100 times more efficient gravitational energy engines than stars are. And remember, the sun is 100 million times more efficient than our energy sources on the Earth. So humans are pretty pathetic in the scale of the universe and how we get energy. This is the way you would get energy, incredibly efficient. And so they're spectacular for that reason, and we're studying. The M87 black hole, just to put it in context, this compares it to the size of the solar system and our most distant message in a bottle tossed outside the solar system. So this is a black hole that's, has this mass of a small galaxy, 7 billion times the mass of the sun, squashed into a region not much bigger than the solar system. And the event horizon at the edge of the dark circle, that event, because of the angular momentum, that event horizon is probably moving at 80% of the speed of light. So just imagine something that size and that mass spinning at 80% of the speed of light. And what does 7 billion solar masses even mean? Well, let's just step up the scales of black hole mass, because again, astronomers, we do it too. We talk about billions and billions, and we just get used to those numbers. But you need to digest what that means to put 7 billion stars worth of stuff into the solar system, or something not much bigger. So here's a sort of modest-sized black hole we start with, and then we'll scale up a couple of times to get to the big one. So this is what we would call an intermediate mass black hole, the kind we found in the edge of the Milky Way galaxy. Maybe the size of a planet instead of the size of a small town. So that's about 1,000 times the mass of the sun. Like I said, nature makes black holes of all these different masses. But what about the big one? Now, we're not using M87, we're using a different big black hole, but there are a number of billion solar mass black holes known. And while you're seeing it, how does this happen? We think that the black holes at the center of galaxies must have formed around the time the galaxy started, and they grew together. So over 14 billion years, black holes and galaxies in the universe have grown. It didn't all happen this quickly. It took 14 billion years, so it could happen. It could happen gradually. Yeah, that's 20. That is the record. The record black hole is about 20 billion times the mass of the sun. So the other new discovery, not as new as that image of the black hole you just saw, but only a couple of years old and very spectacular, is, as if we needed any more absolute proof that black holes exist, LIGO, the Laser Interferometer Gravitational Observatory, showed that they exist. When this signal was measured a couple of years ago, it's called a chirp signal because if you translate it into frequency, it's in the mid-audible range, basically, like the middle part of a piano in a crescendo. And these signals detected with a 7 millisecond time difference, which reflected the difference in time of a gravitational wave crossing between the two LIGO sites, represent the merger of two black holes that are each a few dozen times the mass of the sun. A spectacular event that opened up a new window onto the universe. And again, because these signals can really only come from black holes combining, there's no other way to explain it. So again, unequivocally, black holes exist. What LIGO is doing in cartoon form is two vacuum cylinders, each 5 kilometers long, very, very good, almost as good as the best lab vacuum, lasers bouncing along each tube, And when a gravitational wave, which flexes space-time, remember, space-time is invisible, it's nothing, and yet in a gravitational wave, predicted by general relativity, space-time flexes in all the ways it can. It flexes sideways and longitudinally. It flexes in all three dimensions. And that means anything in the space, like a physical object, is flexing too. But even the vacuum is flexing, space-time out there beyond, between galaxies. And so the instrument is flexing, and if you make the two arms orthogonal, they will each measure different components of the flexure. And so what LIGO is doing by bouncing lasers up and down the arms and trying to see the way the arms are differently squeezed by a gravitational wave in an interferometer is it's measuring this tiny space-time distortion. By tiny, so this is an instrument that's miles across that's measuring a space-time distortion that is smaller than a proton. That was the experiment. It's amazing that it could succeed, but it did succeed. This is what you would see if you could be close to two big black holes. Not big, they're a few dozen times the mass of the sun. So these are dead star black holes. We can't get close enough to black holes to see what happens when they merge, but this is what it would look like. And all these distortions of the surrounding stars are that gravitational lensing effect. So this is a pretty accurate simulation of what would happen. What LIGO is looking at is not the visible picture of that, which we couldn't make anyway. LIGO is looking at gravitational space-time ripples. And this is a visualization of those essentially invisible waves. As the black holes merge, that little crescendo was a cacophony of gravitational waves here, sent out into the universe, traveling at the speed of light for over 1 billion years to reach us and be measured by that instrument. So it's an amazing experiment. They've since detected another 8 binary black hole mergers, and when LIGO comes back online in less than a year, its sensitivity should be at the level where every week, where it's going to get old hat. Every week they'll be talking about a new black hole merger, or neutron stars merging, or neutron stars merging with black holes. When any of the two compact types of objects in the universe merge, they send out a torrent of gravity waves, and LIGO can detect them. But what about the big black holes? Well, LIGO doing its incredible job, which resulted in the Nobel Prize being awarded to the architects of that experiment just 2 years ago, has given juice to some very ambitious experiments to measure gravity waves in space. So if you think of a black hole as a physical object that oscillates and rings like a bell or an organ pipe, then bigger black holes will ring with lower frequencies than small black holes. And it's linear with the mass. LIGO can only detect the ringing and merger and oscillation and gravity ripples of small black holes. The big ones at the centers of galaxies are millions or billions of times bigger, so their oscillations are millions or billions of times slower. That means one of their space-time ripples might take months or years or decades. And there's no way you can do that from the Earth. You don't have the sensitivity. And so you see in the middle and to the left in this diagram, people are conceiving of space versions of LIGO, satellite versions in the super quiet, super still environment of space that will be able to detect the massive black holes of the universe merging and combining and growing from the Big Bang till now. An incredible experiment. And if LIGO had not succeeded, these projects would never have had a chance of funding. They're so audacious, so ambitious, so difficult. But LIGO having succeeded, there's now budget. The Europeans have put serious money. These are multi-billion euro missions, and they are going to be funded. So this is very exciting science for about 10 or 15 years from now, which will look at how big black holes have grown in the universe and combined. Because astronomers think that galaxies in the universe grew by initially being small and then gradually merging and combining to form bigger galaxies. And logically, if every galaxy has a black hole, then when the galaxies combined and merged, the black holes combined and merged and grew that way by combination, by addition. And these space experiments will actually show that happening. They'll also possibly show which came first, the galaxy or the small seed black hole that formed. And we don't know the answer to that. That's an open question.
Believe me, I've been waiting a long time for someone like you to record this moment.
Thank you, Doctor.
Then I'm ready. Ready to embark on man's greatest journey.
Certainly his riskiest.
The risk is incidental compared to the possibility to possess the great truth of the unknown. There, long-cherished laws of nature simply do not apply. They vanish.
And life?
Life? Life forever.
So, now at the end of my talk, I want to address two issues that concern people or are relevant to black holes. They're just out there and it's nice to know about them, but what about black holes and mortality, the issue of creating black holes and death? Well, it's known and been written many times that if any of us, fell into a normal stellar mass black hole, you'd be spaghettified. And that's a pretty unpleasant fate, because that's not like a Stretch Armstrong doll that gets pulled from the feet and the head. That's being stretched at the level of muscles, tendons, molecules. Probably an excruciatingly painful way to die. But if you work it out, any black hole more than 1,000 times the mass of the sun, of which there are plenty, the gravity is strong, but the stretching force is not as strong. And so above that mass, you'd probably feel a little queasy, but you would not be ripped apart. So yes, you can survive falling into the bigger black holes in the universe, in principle. And so it becomes a question. Could it happen? Could it be done? It would be a bizarre experiment, because as seen from afar, you would appear to slow asymptotically. Your light would be redshifted, and you would never actually reach the event horizon. The people who went with you to watch you fall in would get bored and go home, because your time would be running slowly, asymptotically and infinitely slowly at the event horizon. However, to you, you would fall in just on a straight trajectory through the event horizon to an unknown fate. Bizarre difference in perception of the observer and the person falling into the black hole. Wouldn't it be nice to test that? Of course, you still wouldn't be able to get the information out because you've passed through the event horizon. So this idea of surviving a black hole, if it's big enough, is interesting. This is what the journey would look like. So this is not, again, a cartoon or anything. This is a general relativity simulation or general relativity calculation showing on the left, you can see the spiral trajectory towards the event horizon, which is the red boundary. And this is what it would look like from your spaceship as you are falling in. Let's make it a big black hole so you're going to survive this. And all of these distortions, all of the hot gas that's near the black hole and the accretion zone, this is what it would look like, all caused by gravity. And finally, as you hit the event horizon, the universe is lost to you. You lose view of the rest of the universe. It's no real way to sum up the experience, but this is what the physics would suggest. Wouldn't that be an amazing experiment? So I'm going to leave you with a thought. I hope I've reassured you the world is not going to be destroyed. We do not have the technology to make black holes, large or small, but they exist in nature. And I hope I've tantalized you with the possibility that black holes are objects of true inspection and discovery in some distant future where we do have the ability to travel through space, thousands of light years, okay, that's not around the corner, then the experiment can be done. And it does, in some bizarre way, offer immortality to the person who falls in, because if they do that experiment, you go with your buddies and we're all gonna die, so why not do it by falling into a black hole? You go out with all your friends and your family, you have an incredible party in a safe orbit far from the black hole, you go into the black hole in a nice spaceship with a big bubble dome, you wear your best clothes, you make sure you're looking pretty nice, and you fall towards the event horizon, and then you probably time your salutary final wave, because your time will slow down to zero, and so you'll be frozen in your final wave. as seen by all the people that came out. And once they've drunk all the beer and they've got bored, they then go home and you're immemorialized on the event horizon of the black hole. That's pretty cool. Okay, well, what about the rest of the time of the universe? So rather than making black holes objects of fear and death, let me offer them as hopes for sustenance for life and immortality in the future of the universe. Now, this is a future far beyond us. In about 1 trillion years, all the stars in the universe will be dead. Don't get sad about that. Don't get all sentimental about stars, whatever. They're just stars, You can get your energy lots of different ways. You don't need a fusion reactor sitting there in the sky. The cycle of star birth and death that's caused stars to form through the history of the Milky Way will eventually be broken because the stars will all form stellar remnants, white dwarfs, neutron stars, black holes, and there won't be enough gas to make new stars. And the lowest mass stars will die last, the red dwarfs, but eventually all the lights will go out, like a big rheostat turned down, not on our galaxy, but on every galaxy in the universe. So the universe will go dark in 1 trillion years. And eventually, according to physics, normal matter will decay, solar systems will evaporate, the planets will spin off into interstellar space, galaxies will evaporate, the stars will spin off into intergalactic space, and the universe will turn into a thin, uniform gruel. This is the victory of entropy, the second law of thermodynamics. The exception is black holes. They will be the last concrete objects in the universe. And so advanced civilizations of the very, very far future will naturally use black holes to run their lives and their civilizations. For they will be the stars of the far future. And in the intermediate future, between 1 trillion years, 10 to the 12, and about 10 to the 50 years, stay with me on this, these are long time scales, it will be easy to extract energy from the black hole by judiciously dropping in probes and retrieving their energy or angular momentum. So essentially what you're doing is tapping the rotational energy of the black hole. And so in this intermediate long-term future, civilizations around black holes, because that's where they'll congregate, that's where the gravity power is, will be able to run their civilizations and run their wireless internet and whatever else they do using rotational energy of black holes. But eventually the black holes will spin down. And so in the far future, they're left with a much more subtle form of energy. And that's in a universe where everything is a thin, uniform, super low temperature gruel of positrons, electrons, and super low energy photons. The energy remaining will be the Hawking radiation of the black hole. And so an enterprising civilization will build a Dyson sphere, an energy trapping sphere, to capture that feeble Hawking radiation. And in logical terms, the last black hole to survive will be the biggest black hole. And the number on that is about 10 to the 100 years. That's how long it'll take the biggest black hole in the universe to finally evaporate. And that is all she wrote when that happens. And so the last image I'll leave you with is of a super advanced, super far in the future civilization that's huddled around the last black hole in the universe, warming their hands by what's essentially a kilowatt of power from the Hawking radiation. It's not much, but they'll be efficient with it. And they look at each other and they say, 10 to the 100 years, we gave it a good run. Thank you.